So in most of the questions you've done, you're given the molecular formula of the compound as a baseline on which to then use the spectroscopic data to figure out what the actual structure is. The complication in this question is that it doesn't directly give you the molecular formula, which you are going to need really to figure out the structure. You've got to figure out the molecular formula from elemental analysis data. So you learn how to do this in the first year. But if you're a bit rusty with that, then this is actually useful revision on that thing that you may have to do in this kind of context or just as a standalone problem. So you can see that the information you're given is what happens when you burn 0.2 grams of the compound. And what happens then is that every atom of carbon in that 0.2 grams will end up as a molecule of CO2. So the moles of carbon atoms in our 0.2 grams is just equal to the moles of CO2 produced. So we can work that out first of all. So let's just do that and say that moles of carbon is equal to the moles of CO2. And we can easily work that out because we're given the volume of CO2 produced measured at room temperature and pressure. And we know that that's easily turned into moles because that's just equal to the volume in dm cubed divided by 24.0. Okay, so plug the numbers into that. 286 cm cubed is 0.286 dm cubed. So divide that by 24.0 and we get 0.01192 moles of carbon. So then we'll turn to the hydrogen, and again every single atom of hydrogen is going to end up as part of a water molecule, but of course it takes 2 hydrogen atoms to make each water molecule, and therefore the moles of hydrogen atoms will be twice as many as the moles of water. So you've got to remember that factor of 2 here, and you can see that that makes perfect sense just because the hydrogen atoms have to pair up to make water molecules, so you'll only get half as many moles of water molecules. So that's the basis for our calculation, 2 times the moles of water, and we're given the mass of water, so that's easy to turn into moles, obviously. So that's just 2 times 0.1, well, 2 times the mass divided by the relative molecular mass, which is going to be 2 times 0.171 grams, we're told, and the relative atomic mass of relative molecular mass of water is 18, so that's going to come out to be 0.0190 moles. Okay, so now the extra complication that you've got is that compound D doesn't just contain carbon and hydrogen, it also contains oxygen. And the elemental analysis doesn't directly tell you how much oxygen is there, but you can work it out because we know how much carbon and hydrogen we've got. We just work that out, and therefore we can work out what the total mass of that carbon and hydrogen is, and it's going to come to less than 0.2 grams. And the difference is the mass of the oxygen that was in there. So we can find that and then turn that into the moles of oxygen, and then we'll have the moles of each element, and that's going to let us get the empirical formula. So let's go ahead and do that and work out the mass of each element. So if we start with the carbon, we get that the mass of carbon is just equal to moles times relative atomic mass, which is 0.01192 times 12.0, which comes to 0.143 grams. And similarly for the hydrogen, for the mass of hydrogen, again is equal to moles times AR, which is 0.0190 times, which is obviously just 0.0190 grams. So therefore the mass of carbon plus hydrogen is just equal to the sum of those two, 0.143 plus 0.190, which comes to 0.162 grams. And as we anticipated, that's less than 0.2 grams, and the difference is the mass of oxygen. So now we can work that out. So the mass of oxygen is the total mass of D we had, which was 0.2, minus the contribution from the carbon and hydrogen, which is 0.162, and that difference comes to 0.038 grams. So we can now turn that into moles and get the moles of oxygen. So the moles of oxygen is equal to mass over AR, which is equal to 0.038 divided by 16.0 for oxygen, which is going to come to 0.002375 moles. So now we've got the moles of each element, and so we can just use the standard method to turn that into an empirical formula. So you remember that the quickest way to do empirical formulae is normally to do a little table. So we can put our elements here, carbon, hydrogen and oxygen, and just copy those data in. We've got the moles, so we can just copy those in. 0.2 moles of carbon, 0.0190 of hydrogen, and 0.002375 moles of oxygen. And then remember, what you do is you get those in sort of ratio form by dividing through by the smallest of the numbers you've got. So we just say, right, let's divide by the smallest, which is, obviously you can see the moles of oxygen. So we're going to divide each of them through by 0.002375, and the numbers should come to be close to integer values. They are unlikely to be exactly integer values because obviously there are rounding errors that have compounded along the way here, but they should be close to them, and indeed that's the case here. So you get 5 and 8 and 1, and so that just gives us then our empirical formula. So we can say, right, great, the empirical formula is just the expression of those relative numbers of moles, which is C5H8O. So we've got the empirical formula, but remember that's not necessarily the molecular formula. So that's our next mission, is to work out what the actual molecular formula is. So we've got empirical formula is C5H8O. If we calculate the MR based on that, we can easily get a value of 84. But remember that the molecule could actually be, for example, two lots of that, C10H16O2, or any multiple of that. So we need to know what the actual MR is, and then we can work out which multiple it would be. And that's where the mass spec data comes in. So remember that in the mass spec, the peak with the largest value of M over Z we consider for A-level purposes to be the molecular iron peak, and that gives us the MR. So in this case we don't have to look at the spectrum because it just tells us that the molecular iron M over Z is equal to 84, and you can see that's the same number. So that's what we needed to know. So this means that the actual MR 84.0 was 84, and therefore that means that the empirical formula is the same as the molecular formula. Okay, so if the molecular iron had come out to be 168, then you'd know, oh, it's 2 lots of C5H80, but it's the same, so that's the actual correct molecular formula. So we've now got our molecular formula, and so now we can start looking at the rest of the spectroscopic data. So it tells us the infrared has a peak around 1700, strong peak around there. You're very used to by now. That's one of the commonest peaks that you find is a carbonyl peak. So we can write that down. Infrared peak around 1700 is C double bond O, and just quote the datasheet values just to sort of back up that statement. So it tells you 1630 to 1820 wave numbers. Okay, so we know it's got a carbonyl group, and then we've just got this very small amount of proton NMR because it's telling us, well, all we've got are 2 triplet peaks at 1.0 and 2.7 ppm, and we have to assume, I mean, the question's not exactly clear, but we have to assume that means that's all there is in the proton spectrum. So in proton NMR, 2 triplets. What does that mean? Well, remember, a triplet means that you've got 2 hydrogens on an adjacent carbon. And if you've got 2 triplets, that means you've got 2 sets of adjacent hydrogens splitting each other. In other words, 2 triplets means that you have a CH2 next to another CH2. And obviously, because carbon must have 4 bonds, that means there's 2 things coming out the ends of that. So there must be that unit in the structure, and you just explain that's because there are each CH2 gives a peak, which is split by the 2 hydrogens on the adjacent carbon. So we know we've got that, and we also know that those 2 CH2s must be in different environments from each other, because obviously otherwise they would all just collapse into one peak. So if we've got 2 separate triplets, then we must have 2 non-equivalent CH2s like that. However, there are 5 carbons in the molecule. One of them is the carbonyl carbon, so there are still 4 carbons to account for. So the only way that we could only have those 2 CH2s is if you've actually got 2 lots of that unit. In other words, we can say that there are 4 carbons to account for addition to C double bond O. And the only way we can comfortably do that is to say that there must be two equivalent CH2 units in the molecule. In other words, what we're looking at is symmetry. So that would mean that we had this basically. Which is fine, and what we do then is say, well, what are we left with that we can use to say what goes on the ends of those? And the answer is, well, nothing at all. We've actually then accounted for all of the atoms in our C5H8O molecular formula. So the only way we can turn that into a complete molecule is to bend it round and form a ring, so that those two CH2s at the ends, which at the moment are each lacking something to bond to, can bond to each other. So we can say this fully accounts for all the atoms. So the complete molecule, the only way we can get that is to bend that round and form a ring. So we'd have CH2, CH2, CO, and then CH2, CH2, CO, and these two CH2s, crucially, would now just be bonded to each other. Okay, so that's our molecule. And what we should do then is just check the assignments, because we've got the chemical shifts to account for. So these two CH2s, this one and this one, are equivalent. They are next to a carbonyl group, so those have an HCCO shift, which is about 2 to 3 ppm. So that accounts for the peak at 2.7. And then the other two CH2s, so this one and this one, again are equivalent to each other, and those have just got other CH2s next to each other, so you have an HCR shift, which is 0.5 to 2 ppm. And so that's consistent with the peak at 1.0. So they give the peak at 1.0 ppm. Okay, the one thing that might puzzle you is, what about the splitting of those CH2s that give the 1.0 ppm peak? Because you can see they've got, when you look at their neighbouring CH2s, it looks like at first sight you might think the splitting is going to be more complicated than this, because here's our, this CH2, in other words, has got CH2 this side, and it's also got a CH2 that side. So you'd think, right, well, it's going to be split by those, and then it's going to be split by those. So it's going to be split into at least 5, and possibly more if the splitting's not equivalent from these ones and these ones. In other words, you could have complex splitting. But you have to remember the key thing, which is that equivalent hydrogens don't split each other. That's just a rule that we learned. It's not easy to justify that at this level, so you just learn that equivalent hydrogens don't split each other. So this CH2 will be split into a triplet because it's got the CH2 on this side. The CH2 on that side is equivalent. These two are equivalent to each other, so they don't split one another. And so you're just left with splitting into a triplet. And obviously the same would be true for this one, which would just be split by that. So the triplet is correct, but it's worth noting that that's why it's only a triplet. So I'll just note down equivalent CH2s don't split each other. Okay, and so that's our complete answer. So just in summary then, what we've got is cyclopentanone, which is that which fits the complete bill.